paste. Mu p is 2. Okay. Okay. Here for the doping, we must set doping donor density for TiO2 as ETL 1E18 and 0 for Na. That guarantee this is pure donor semiconductor material or N-type material. 1E18 for defining the you don't see the doping density here, but in the domain I can click right and use the doping. We have two options: analytic doping model or geometric. I use analytic doping. Geometric is the related to geometry, and it can be varied by the x position, y position, and it's related to your dimension of your study. Here I choose 1E18, 1 divided by cubic centimeter. Okay, and impurity type must be donor doping. Okay, 1E18. Okay, I choose ETL, and also I can write the ETL N type. Okay. Okay. I continue. The other parameter don't need here. The absorption constant A and B. It's for absorption and optical properties. It's about the generation rate that we don't want to investigate here. We choose a constant generation rate for simulating a IV curve, but we don't want to simulate optical properties in this tutorial. But in the later tutorial, we will talk about the optical simulation with the COMSOL Multiphysics. Okay. Here, but electron and whole lifetime is important. For this means, in the domains, I right click on domains, I choose generation recombination, I choose trap assist recombination for electron transport layer TiO2. Here we can choose Shockley-Rittal model or explicit trap distribution. I use Shockley-Rittal model. Tau and tau p, it can be defined from material. Delta E trap energy also can be set. Here I choose a simple value 0 electron volt. Tau and tau p was by clicking here, these values are appear here. 5 nanosecond, the right value for this parameter. Okay. Also we can choose this geometry, other geometry for this approximation. Okay, let us to define the PVK material property for PVK or MAPBI3. Electron affinity was set 3.6, 3. Excuse me, electron affinity 3.6, capital V. Also, we can we can uh, don't write don't write the unit, because the unit in this column default was capital B, but for exercise we define this. Okay, the band gap was set 1.52. The electric permittivity was set 18. The conduction and valence band effective density of a state was set 5E18. Both are the same. Let's check out the okay PVK 5E18, 1 divided by centimeter cubic centimeter, and C and NV. Okay. The electromobility for electron hole are set to 2 square centimeter divided by volt multiply second. Okay, I copy and paste. Tau n and tau p for the perovskite was set to 100 nanosecond, 100 nanosecond. Okay. For HDL, let me introduce. The affinity, electron affinity was set 1.9, and band gap is 3 electron volt. .9. The electric permittivity is at 3. Okay. The conduction band effective density and valence band effective density was set to 1A20 a square per 1 per square centimeter. Excuse me, cubic centimeter. Is 20. 1E20 1 per cubic centimeter. The electron mobility was set 2 and hole mobility 1e minus 2. squared centimeter divided by volt multiple by second. Also for whole mobility, this unit are the same. Tau n and tau p for spiral is set to 5 nanosecond. Okay, and the donor and acceptor density, I must check for HTL. The acceptor density was set to 1e18. Let to introduce the domain, domain, double click right on doping density, HTL p type. Okay, here I use acceptor doping 1e18. Okay, here we have defined almost all parameter, but please consider that the basic physics tell us about the intrinsic semiconductor. Here NA is equal to 0. That is not necessary to define in the COMSOL or any software. It can be used as the intrinsic semiconductor that, and also we can choose ND and NA equal to any arbitrary values, but this 2 is divided and will be 0 because the ND minus NA will be solved in the basic equation for the Poisson equation. Okay, here I must choose two contacts by metal contact, by click right and boundaries, metal contact. Here we have FTO contact. We can choose ideal ohmic as FTO contact. Okay, also I can choose another metal contact and AU contact. Okay, also I choose ideal ohmic for this values. Here I must define a voltage for sweeping on any contact that I want. By sweeping this voltage, we can read the current density. By reading the current density, the IV curve will calculate it, and also we can extract the short circuit current, open circuit voltage, and fill factor, and finally the efficiency of this device. Okay, for example, I choose FTO contact. It depends on your definition. I use here as applied voltage V minus app. We underline app. I define this value V app 0 volt. Okay. In COMSOL on and also in many software, also your codes, you can sweep it by using parametric sweep or auxiliary sweep in your study. I choose a study, I add a study, a stationary study. Okay, here I can choose study extensions. I click on auxiliary sweep, I add it, I add the V app. For varying this value, I choose the code of range, a range from 0 by 1.0.01 to 1.2 volt. Before compute this problem, we must define also the generation. The generation comes from the optical uh, section of this device. When the light is on, the photons come to the perovskite layer and absorb. The generation will occur. The carriers will generate and uh, move through the conduction band and valence band. Electron holes will separate, and the drift diffusion current will appear, mm, and the device will working. And okay, here I choose a user defined generation. I can choose the perovskite layer or all two other layers. It's depend on your the generation rate in perovskite is mainly important, than maybe 900% or maybe more generation rate will occur in this layer, because this is absorber layer or active layer. Here I choose for example, we must check it, 2.2E21, 2.2E21. Okay, for all layers, a constant value. I can use a code, or maybe I can simulate by EWFT of physics, microwave frequency physics, and calculate this value. I will teach you in in later tutorials in um, near future. Okay. Before the computing a study, I use a mesh. Let me show you. When you use normal mesh, you can see by physics control, you can see the point that will be used in the equation for solving. Uh, Look at that. You can see the number of mesh point in this region from 148 to 154, that we have 2 points. It may be this mesh is not good for this problem. Let us use a finer mesh. Okay, in the finer mesh, let me to zoom on it. From 149.4 to 150, we have 2 points that assured in each 1 nanometer. In each less than 1 nanometer, we have a point. It may be a good mesh for this problem. Okay, I don't know what will be a result. This is a this for first that I am exercising with you. let me to compute this problem. Okay, from the progress window, you can see the progress and also V underline app that will solve, and it's very good uh, mesh and data values that will solve regularly, and the error bar it's very good, and 10 minus 11 e minus 11, it's a very good error bar for solving this problem. Okay, uh, I will add my email address, my number phone, my WhatsApp. You can call me, you can message for me in my email, in my WhatsApp, Telegram, or my site, and I will help you. I can teach you in private or as a workshop. Just tell me your opinion about this tutorial. Okay, this problem will solve, and it's amazing without any error and convergence failure. Look at this. The console will show you the default window, for example, energy levels, carrier concentration. Uh, we can work with this uh, data. For example, I can choose a arbitrary voltage that the band structure will show 0.02. Here you can see by varying the applied voltage, the band structure will changed. Okay, uh, the most problem the uh, practicer with the COMSOL for calculating current density is that maybe some guys use the uh, linear or point graph for calculating the current density, but it's not correct. We must choose a one diploid group, and by right clicking on it and using global option, by using the global option I can choose the codes of uh, terminal current, for example semi I01. I can plot it. Okay, or maybe if you choose a wrong contact, the current maybe it's not good. Let me to change it to semi I2. Okay, here we have this behavior of current density. Maybe it's not okay. This is a current, not current density. Let me to divide it by area as we defined in parameters. I also change the unit to milliampere per divided by a squared centimeter. Okay, the final results of current density versus voltage, it is shown here. That is not similar to uh, this paper or any conventional paper. I expect that this current density will appear, but not seen here. It because of the generation as I experience in the simulation. Let me to choose higher values, for example 2022, as you can see the current is very low. It's about 1e minus 5. Let us to compute it again. You can see the last computation time here. My computer uh, has a 16 gigabyte RAM and 7 CPU, Core i7, fourth, excuse me, 5th generation, and Intel and AMD graphics. And you can choose a better computer to have a quick simulation. Okay, here as you can see the error versus iteration number is very good. Let us to run it again. Okay, the current still is low. Okay, let me to choose a higher values. Okay, you can choose a centimeter. By choosing centimeter, this value would be very high, and we can run it again and compute the current density versus voltage. Okay, let us to see. Let me show you progress. You can see the progress, the percentage of progress, and applied voltage changing, and convergence plot. Okay. Okay. Also in this message, in the message box, you can see the number of degrees of freedom that considered for this simulation. Okay. As you can see, the current will enhance significantly to 146 milliampere per divided by a squared centimeter. Let us to use lower values and run it again. Okay, the converger plot is still in a good form. Also applied voltage and other thing it's working properly. Okay, now the current density is it's very good. It's because let me to choose semi ISF I02. Also we can choose minus semi I02 or I01. It's related to you. It will it's better for us. Maybe semi I01. Uh, maybe it's better to choose AU contact for applying voltage. Let me choose this contact. Okay, and do another simulation. Okay. Okay. As you can see, when we change the contact, the error bar uh, was changed, and this pattern was differ from the previous pattern of the error. Okay, let me show you current density. Okay, it's very good. As you can see, the current density. Let me to zoom on it. The minimum x and maximum x. Is better to 1.1 from 0 to 20. Okay. 22. Okay. 1.2. Okay. As you can see, we have the current density versus voltage, which is very similar to these values, and we could run this problem. Okay, now our tutorial uh, is finished, and also you can contact with me with this contact information merkostarpaju@gmail.com merha.minbashi@gmail.com WhatsApp plus 1998 939 50 16 731, or my site merkostarpaju.com or Google Scholar. I can be in touch in any time with you. Okay. Uh, have a good time and be careful. Bye bye.